we now move on to our next integration technique, which is integration by parts. And again, this is going to be inspired by a derivative rule, in this case, the product rule. And the product rule states that the derivative of the product of two functions, in this case u and v, is going to be the derivative of the first function, u prime of x, times the second function, v of x, plus the first function, u of x, times the derivative of the second function, v prime of x. And if that derivative relationship holds, that actually tells us that u of x times v of x must be the antiderivative of the right-hand side. So u of x times v of x must be the antiderivative of u prime of x times v of x dx plus the antiderivative of u of x times v prime of x dx. So now what we're going to do is we're going to rearrange the terms so that what we have is the integral of u of x v prime of x dx. In that case, if we solve for that integral, we must have u of x times v of x, and then I'm going to bring the other integral over to the other side, so that's going to be minus the integral of u prime of x v of x dx. Oftentimes, they like to switch the u prime of x and the v of x, so they like to write v of x u prime of x dx. And this is going to give us the classic integration by parts formula. Okay, so this is going to be written as the integral of u, and then we're going to rewrite v prime of x dx by thinking about v prime of x as being dv dx times dx. And so a lot of times they like to pretend that the dx's cancel. They don't actually cancel, but they like to pretend that they do. And so they really write this as dv. So the integral on the left becomes the integral of u dv. And then on the right, we have u times v minus the integral of v, and then u prime of x dx is going to just be called du for shorthand. And this is the integration by parts formula the way it's generally written. Okay, so we've justified the formula, but we haven't really seen how it works. Okay, so I'm going to need to do a couple examples. So I'm going to start with the integral of x times e to the x. And the first thing you should realize is that you can't really do a substitution because I don't see a composition of functions here. X is not a composition of functions, and e to the x isn't really a composition of functions. So I've got to try something else. What I really see is the product of two fairly simple functions. Okay, so one of these I'm going to label u, and the other one I'm going to label dv. So u is going to be x, and dv I'm going to call e to the x. Now, why did I choose u to be x and dv to be e to the x? Well, dv, which is e to the x, that's easy to integrate because the antiderivative of e to the x is going to be e to the x. In fact, we often write dv as e to the x dx, and then the antiderivative is just e to the x. And then u is x, and I'm going to be differentiating u to find du. And du is just written as 1, okay, or 1 dx. And I'll notice that the du is now simpler than u was, because by taking the derivative of x, I now just have 1 there. Okay, and that's generally how you choose which one is u and which one is v. We want to take the derivative of u and make it simpler, and then we want dv to be something that is easily anti-differentiated. Okay, so we're going to use the integration by parts formula, and that formula says that this integral of u dv is equal to u times v. So u is x, and v is e to the x, minus the integral of v In this case, v is e to the x. And then notice that du is just 1 dx. Now, remembering the formula for integration by parts, that the integral of u dv is uv minus the integral of v du, that's a hard thing to do. So I always write out the little chart like I did for you just there. And then what I do is I draw a 7. So I draw a line between the u and the v. And then I draw another line between the v and the du. Draw a little 7 there. Okay, and so then what that does is it diagrams out what the integration by parts formula is. So u times v, that first line that I drew, is the x e to the x, and then minus the integral of v du, that's the second line of the 7, v times du. And so sometimes I call this the lucky 7 rule, because that is an easy way to remember the integration by parts formula. Okay, so now I have that the integral of x e to the x is x e to the x minus the integral of e to the x dx. So I need to do one more step. Okay, that's x e to the x minus, okay, I'm now going to take the integral of e to the x and get e to the x again, and then I'm going to add c. Okay, if you really feel like it, you can simplify this. Make it x minus 1 times e to the x plus c. And that's our first example. Okay. Now, our second example is one that comes up often, okay, and that is the integral of natural log of x dx. And at first glance, you're going to say to yourself, I don't even see a product of two functions there. So how am I going to use integration by parts? Okay, but this one is kind of a special case. It's a hidden special case. And you can think about this integral as being the integral of 1 times natural log dx. Okay, here I could make natural log of x dv, but I'm going to have to anti-differentiate natural log of x. And that's actually the whole problem I'm trying to do, so that doesn't make sense. So when you get natural logs in these problems, you often find that you're going to let u be natural log. And then dv, in this case, is just going to be 1 dx. So to find du, the derivative of natural log of x is 1 over x. And to find v, the antiderivative of 1 is going to be x. So I'm going to add a little dx here to my 1 over x. Okay. Now I'm going to draw my 7 so I can remember this rule. Okay. That's going to tell me that this rule is that it's x natural log x minus, okay, the integral of v du, so that's x times 1 over x dx. Okay, so that's x natural log x minus the antiderivative of x times 1 over x is 1, so just of dx. So now I'm going to get x natural log x minus the integral of dx is just going to be x, and I'm going to add an arbitrary constant c. Oh, but I just noticed that this problem is actually the integral from 1 to 2. So I'm going to need to add in the limits of integration. And this is a good time to show you how that's done. Okay, so I'm actually going to put in the limits of integration right here from 1 to 2. And then carry them forward in this integral from 1 to 2. Okay, so I'm going to leave them there from 1 to 2. And then this is going to be from 1 to 2. Okay, so let me go ahead and put in those limits of integration. Okay, so I'm going to get 2 natural log 2 minus 1 natural log 1. And then the integral of dx from 1 to 2 is just going to be 2 minus 1. Okay, so in fact, I'm going to get 2 times natural log 2. Okay, let's remember that the natural log of 1 is 0. So then I'm going to get plus, minus 2 minus 1. That's better because I was subtracting that integral. And so then I'm going to get 2 natural log 2 minus 1 there. So now I've done this one by finding the antiderivative, but I also wanted to do it with the limits of integration. So in general, when you're doing these problems of integration by parts, u is usually the thing that you want to take the derivative of. So you're hoping by taking the derivative of u that you'll make the expression for u simpler. Okay, so u is often going to be powers of x for that reason. And then for dv, it's got to be something that you can easily integrate. Okay, so dv often is going to be things like it's going to be things like e to the x or sine and cosine, which are easily integrated. Okay, but dv is not usually going to be powers of x, because if you integrate a power of x, you're going to get something like 1/2 x squared, which is more complicated. The only time in which this is different is when you're dealing with natural logs. In that case, natural log x is usually u. And then if that's multiplied by a power of x, like x squared or something, that's usually the dv. So I've left you with many problems that you can work out as examples, and we'll be working on those problems in groups together.